Hi, my name is Dayi Ethan Dong, and this summer I did work on ergodic exploration of meshable surfaces under the advisement of Dr. Jordan Couteau and Dr. Howie Chaussett. So the motivation behind this work is effectively to perform satellite inspection. So the goal is to be able to localize failures along the satellite and optimize this trajectory with respect to various criteria, particular time and fuel. We'd also like to be able to input some sort of prior information about where these failures may occur. Looking at some previous work, we see that ergodic search is a search algorithm that has already been researched previously. This sort of algorithm optimizes the trajectory of the robot to spend time in areas of higher information, and this information is generally available through what's called the information map, which is effectively just a probability distribution. This method also introduces what's called the ergodic metric, which is just a scalar value that determines the quality of inspection of the trajectory. Essentially, this metric measures the difference between the fraction of time spent in a region and the information actually in that region computed in the Fourier space. Now we define the actual ergodic metric that is used in the ergodic search formulation. Here we define it as epsilon e as essentially just the summation of ck minus vk squared, where ck is the Fourier transformation of the time average trajectory statistics, and vk is the Fourier transform of the information map. So breaking these down, you see that second equation actually breaks down ck and vk into their formal definitions. Now, looking at the optimization formulation shown in the bottom, we see that we're trying to minimize the ergodic metric epsilon, and as well as minimizing the controls u. These are also subject to the constraints of the dynamics, being that function f, and initial position and velocity constraints, as well as a collision avoidance constraint in the bottom, where effectively we're just trying to keep the robot that is searching over the area away from the surface that it's searching over. Next, looking at mesh approximation, we use triangle meshes because they are a standard way to approximate 3D geometry, and we specifically use TriMesh, which is a Python package that can help us manage these meshes into objects by taking an STL file and creating it into a TriMesh object. Now, looking at 3D search, something that has also been done, prior work that did ergodic search on surfaces has always been doing them on simple surfaces with analytical solutions for the basis functions. So this is a sphere, a torus, or even just a 2D plane. Prior work has also done uniform coverage over more complex surfaces, as you see in the bottom right, through the use of pre-planned waypoints, where each of these waypoints effectively has its own defined coverage of the surface. So the goal that we're trying to tackle is to perform ergodic search over a 3D surface or object, for example, a satellite or a plane, and we want to use a mesh approximation of that surface alongside a sensor model on the robot that effectively collects our information. We also want to be able to validate this against existing solutions of standard ergodic search, where we have the available analytical solutions for the basis functions. We also want to test this algorithm on a variety of different manifolds that are a little bit more complex. In our new approach, we come across another problem, though. The issue is that the ergodic metric only seeks to match the distributions between the trajectory and the information map, and it doesn't optimize for more observations when a sensor cannot be collecting data by facing away, for example. So we introduce a new metric called the observation array. The observation array is effectively a matrix of time steps along the trajectories by vertices in the mesh, where each value in this matrix represents how much the sensor is seeing that vertex at that point in time. And this becomes a better metric of the total observation, since we want this array to basically be as large as possible. So, including this into our approach, we generate a mesh of the 3D manifold surface, where we need to effectively calculate the CKs, which is the Fourier transform of the time average trajectory statistics, which we can approximate as such, where B is the approximate basis functions computed from the mesh, F is the observation array from the sensor itself, and the delta A is the weights for the vertices in the mesh, since it's not always uniform anymore. So independent of this area term delta A, we still need to appropriately weight the observation array so that it can be at the same scale as the information map. Otherwise, it is impossible to compare these two distributions. And we can accomplish this by using the mass matrix of weights for the mesh vertices, and the mass matrix is effectively a way for us to tell how much each vertex has in area. So we also need to generate an initial trajectory, an initial guess for optimization to utilize. And this is usually very sensitive, but it's also sensitive in the normal ergodic search case because the optimization really is only able to find a local minimum. So for our problem, we also need to find a decent initial trajectory that we see in the bottom right-hand corner. So going on now, we're able to test this on simpler and current models of the satellite. Simpler model you see in the bottom left, and this more complex model you see in the bottom right, both converge trajectories. And we actually see that we do in fact have an increase of the sum of the observation array. So we go from 7,992 to over 12,600. And of course, these values themselves aren't really scaled to any sort of specific meaning, but we see that an increase does in fact mean more observations being taken. We also see that it satisfies the desired distribution information because the ergodic metrics get smaller, from 1.19 times 10 to the negative 2 to 5.79 times 10 to the negative 3 after optimization. We also compare it to our simple cases, or analytical solution cases, specifically comparing it to the R2 exploration space. So we're comparing it to the normal search that's performed in this 2D Euclidean space. And we see for the analytical solution, we're able to generate a nice trajectory that searches over the area using a specific sensor, specifically a Gaussian sensor. And using our solution, when we approximate this 2D space as a mesh, we're still able to generate this nice trajectory that seems to search the area completely.